Hello everyone, and welcome back. Last time we started looking at rotational motion, and we're going to continue with that today. Rotational motion continued. What we noticed last time is that there were some angular quantities, or rotational motion quantities, that behaved in relation to each other in a very similar way to the translational or linear motion quantities, how they related to each other. For example, we noticed that the position coordinate in translational motion acted very similar to the way the angular position coordinate theta did for rotational motion. Linear velocity v, angular velocity omega. Linear acceleration a, angular acceleration alpha. The linear quantity that caused changes in motion, the force, the angular quantity that caused changes in rotational motion, the torque, tau. What we're going to do is continue and look at some more quantities and how they behave in relation to the translational motion compared to rotational motion. And what we're going to start with is work. How does work behave when we're talking about rotational quantities? Let's imagine that we've got a small mass, m. Now this could be just a single particle of mass, or it might be a small part of a larger extended mass. And let's imagine it is at some distance r from an origin, and we apply some force to it, F, and then there's a displacement ds. So rather than dr, I'll call it ds, like it's part of the circular motion that we've talked about before. So what's the work done? Well, what we need for the work is we need to find the component of the force that is in the direction of the displacement. So remember, we'll call that F sub t, the tangential part of the force. The work done then in this infinitesimal motion, say ds, is equal to Ft times ds. Now ds we already have seen in terms of the change in motion. Here, if this is some angular change d theta, we know that ds is r d theta. So we can write this as Ft r d theta. But then what is Ft times r, the tangential component of the force, which is perpendicular to r, times r? Well, that's the torque. So that is the torque d theta. So we see a very similar sort of form for the work. The work is F ds, or the force displacement, and the work done in terms of a rotational motion, we've got tau d theta. In other words, force is similar to tau, ds similar to ds. Now, we don't have the vector form, the complete vector form of the work, which would be F dot dr in that case. We don't have vector forms for these rotational quantities yet, but we'll get those shortly. What about the power? If we divide by delta t, or dt, this would be ds dt, which would be F times the velocity, Ft times the tangential velocity, to be specific. We divide by delta t, dt, what do we get? We get tau, d theta over dt is omega, tau omega. So for the power, where power is work per time, the amount of work done per time, we again get a very similar form for the translational as the rotational quantities. We get force times velocity, or torque times omega, something very, very similar. What about kinetic energy? Well, let's take a look at that. What's the kinetic energy of this mass? If it's moving at some velocity v, we have that the linear, or I'll say Ke sub capital T for translational kinetic energy, is 1/2 mv squared. But the velocity in terms of the rotational quantities, remember we know v is equal to r omega. So if we've got this object moving around in a rotational motion, we have that v is equal to r omega. So we could write this as 1/2 m r omega squared, or 1/2 mr squared omega squared. But for a point particle, what did we find mr squared was? That's the moment of inertia for the point mass. And so what do we end up with? 1/2 I omega squared. Again, a very, very similar relationship. We've got 1/2 and 1/2. Linear velocity, angular velocity squared. Instead of m, we have I. Remember, m was the inertia that an object has to being accelerated linearly. I is the inertia that something has to being accelerated rotationally. So again, we get a very, very similar result, which tells us that when something is rotating, it has rotational kinetic energy. Okay, very, very good. There's one more thing I want to say about moment of inertia. Let's imagine we have some extended object with a center of mass. Let's say it's there. And when we rotate this object, or when we try and rotate it, it has a moment of inertia. I'll call it ICM. In other words, when we try to rotate it about its center of mass, the moment of inertia is ICM. In other words, the center of mass moment of inertia. But what if we try to rotate it about a different point? Imagine we put our axis of rotation over here, not at the center of mass. So, for example, we might have this wheel, and we might rotate the wheel about its center of mass. The center of mass is right in the middle here, like that. But what if we tried rotating it about a different point that's not the center of mass? So maybe we have some motion that looks like this, where it's rotating about this axis as opposed to this axis. What's the moment of inertia about that axis? Well, it turns out, bring this back, it turns out we can basically, we won't prove this, but we can think of this motion as two parts. Notice what's happening to the wheel. There's two parts of this motion. The wheel is going like this, around in a circle, the whole thing, at the same time that it's undergoing this motion. So if we combine this motion with this motion, what do we get? We get something that looks like this, which is exactly what we're talking about. So it turns out, and again I said we won't prove this, it turns out that the moment of inertia about this axis is equal to the moments of inertia of those two other rotational motions. First, of the whole thing moving around like this, which corresponds to, let's imagine this is some distance h, it's the total mass times h squared. That would be the moment of inertia of something and just moving it like this in a circle without rotating it about its own axis. Just moving it like this around in a circle. Every single particle is going around in a circle of the same radius. A radius, in this case, of h. So that's got a moment of inertia of mh squared. Then, the part of the moment of inertia that corresponds to the actual rotation around the center of mass, we add ICM. So the total moment of inertia about an axis that is not through the center of mass is the moment of inertia about the center of mass plus the total mass times the distance that the axis is from the center of mass, mh squared. This is called the parallel axis theorem. And I should emphasize parallel, meaning that the axis about which we are rotating the object is parallel to the axis through the center of mass that was used to calculate this. So you can't just pick some other arbitrary axis that goes through the center of mass. Here, in order for these to be equal, the two axes about which we're rotating the object have to be parallel to each other. Okay, very, very good. Now, what that means also, and we can think about this then, is when we were talking about the kinetic energy of the object. If we have an object that is undergoing two different kinds of motion, let's say it's rotating and translating, then we can break its kinetic energy down into two parts, like two motions, where there's one motion where the whole thing is moving, and then one motion where it's rotating. So the total kinetic energy would be the translational kinetic energy, 1/2 mv squared, where that v is the velocity of the axis of rotation, or the velocity of the center of mass, plus 1/2 I omega squared, which would be the kinetic energy of the object as it's rotating around its axis of rotation. So we can break the total kinetic energy down into the two parts. Okay, very good. So far, we've looked at the analogy between translation and rotational motion in terms of the position, the velocity, the acceleration, the quantity that makes changes in those, the force and the torque. We looked at the kinetic energy, and we saw that the form of the kinetic energy for translational motion gives us the same value as the form in the rotational motion if we've got, say, a particle moving around in a circle or something like that. What about momentum? Momentum is an extremely important quantity. Do we have a similar sort of relationship between translational and rotational motion for momentum? Well, let's take a look. The linear momentum we found was m times v. Well, maybe we can imagine that we might get something similar using the analogous quantities. The analogous quantity for m is I, the analogous quantity for v is omega. Well, what would this look like for a point mass? So imagine we've got some mass m at a speed v at a distance r from the origin. Does this give us the same thing as this one? Well, let's take a look. What do we have? What is I? I, we know, is mr squared, and omega is v over r. Well, one of the r's cancels, and what do we get? We get mrv. mv is momentum, and so this looks like r times p. And as usual, what we really need is the component of p that is perpendicular to r. So we might say this is v sub t, or p perpendicular, the component of p that's perpendicular to r. Well, it does not look the same. It's not the same quantity. It's an analogous quantity, this momentum for rotational motion, but it's not the same. Not like we found that the rotational kinetic energy, 1/2 I omega squared, reduced to the 1/2 mv squared, the same form as the translational motion. We've got a different quantity here. Well, it's different, but it is still extremely important. This is what we call the angular momentum. And we will represent this quantity with a capital letter L. This kind of breaks with the tradition. It seems like, well, I did too actually, it seems like we use Greek letters to represent rotational quantities, theta, omega, alpha, tau, but here we've got just regular English letters, I for moment of inertia and L for angular momentum. All right, well, very good. But is this a particularly important quantity? We've defined it, but what can we do with it? Well, let's see how it relates to the torque. We know that the momentum, the linear momentum we found, was related to force by the force was dp dt. How is the angular momentum related to the torque?